Right. So just picking right up where I left off in the last recording. So I talked about resistance as a concept, resistance as a property, both of a circuit and of an individual device that we wired into the circuit. And we talked about the effect of resistance on how much current ends up flowing out of the battery through the device or devices, and then finally to the bottom of the battery. And I pointed out that the more resistance to flow that there is in the circuit or in the individual device, the less current naturally flows. Okay, so R is this thing, and eventually we're going to get around to figuring out where R comes from and how to calculate it, but not yet. As I said at the end of the thing, as I said at the end of the last video, let's turn our attention now to the battery. And I want to say ahead of time that I am going to continue to think of this as a battery rather than as Puget Sound Energy or something. But you know, your local power company, whatever your local power company is, the concepts that I'm about to present to you also work for the electricity that's sent to your home. 240 volts AC in Europe, 120 volts AC in the United States, but whatever. But applying the analysis that I'm about to do for you to the electricity you get out of your wall outlets is more complicated. Functionally it's the same, but it's more complicated to do. So let's not go there. Let's just think about it as a battery and not get more complicated than that. All right. So considering this to be a battery, a D cell, so 1.5 volts, or if you prefer, we can have 2 D cells, so just wired in series, so 3 volts. Either way. And again, in previous lectures, I've always just labeled this as V, but I'm not going to do that now because, as I said at the end of the last video, there's something else going on. And it's actually not a dark and bloody mystery anymore, and not since I've introduced the concept of resistance, because as it turns out, and perhaps unsurprisingly, the battery itself has some resistance to flow. Not a tremendous amount, perhaps, not compared to some of the objects that you're trying to operate, like a toaster, but definitely not insignificant, okay? So, in fact, the battery itself, with its so-called internal resistance, is also going to inhibit the flow of charge. The battery itself actually decreases the amount of charge that flows, okay? And so the potential difference, the drive, the force, the electric field, however you want to think about it, that the battery gives to push charge around is actually slightly less than you might guess from the rating that's stamped on the side of the battery. And that's simply because the rating on the side of the battery doesn't, or may not, include or take into account the internal resistance of the battery that's tending to impede the flow of current, okay? So we want to make a distinction then between the potential difference that the battery supplies to the whole circuit versus the potential difference that the battery was built to provide. The potential difference the battery was built and designed to provide is decreased somewhat by the effect of the internal resistance that the battery inevitably has. And so we'll take that into account by giving the battery's potential difference a very different symbol than what we've used before. Before, we used capital V for the potential difference supplied by the battery, but for the reasons I just explained, I don't want to use V anymore, so we give it this symbol, this script E, okay? This thing here, it's very, very similar to a potential difference. It is essentially a potential difference, except that it doesn't take into account the internal resistance of the battery, okay? And as such, it has a slightly different name, okay? And the name that it has is the EMF. EMF, 3 letters, EMF. What's going on here? Well, let me start with this. Let's take this in slow motion here. again, we're at the question, what current is going to flow in our circuit here? Okay, that's the question that we're working on answering. We've already said that the more resistance to flow that there is in the circuit, mainly caused by the devices that we're trying to operate with the circuit, the more resistance to flow there is, and just for short, for now, I'm basically saying the more resistance there is, the less current there is. But the bigger the battery is, let's say that anyway, the bigger the battery is, the more current is going to flow, right? So I'll say I is directly proportional to this EMF thing, EMF. And it's essentially a potential difference, but as I said, it's a potential difference before we subtract out the effect of the internal resistance of the battery. And not only is it essentially, I mean, it is so much a potential difference that in fact it has units of volts, just like a potential difference has. Okay. For most practical purposes, I will tell you this. For most practical purposes, the EMF and the potential difference, which I've always called V before, are functionally the same thing. They're not quite the same thing, and I will explain in detail the difference here in a little while. We're approaching what I need to develop in order to really clarify the difference between the EMF and the potential difference. It is also worth pointing out, and this is just sort of, now this is a long way away, but anyway, I'll tell you now. The other reason that this concept of EMF suddenly appears is because a battery is one way to create an EMF, but it is not the only way to create an EMF. A battery, any more than a battery, is the only way to create a potential difference. There's lots of ways to create a potential difference. All of them have units of volts. They are all symbolized by the letter capital V. There are lots of ways to create EMFs. A battery is only one of those. Okay? And when we study magnetic field, we will discover another way to create an EMF that has nothing to do with electric charge. Okay? At least not directly. So I wanted to warn you, there's two reasons to bring up EMF. One of them is because the EMF is slightly different from the potential difference of the EMF of a battery is slightly different than the potential difference of a battery, again, because of the internal resistance of the battery. Potential difference takes into account, EMF doesn't. The other thing is that there's more than one source of EMF, more than one way to create an EMF, and the other one will be, as I say, when we study magnetic fields. So with all that out of the way, the answer to the question then, what current flows, is really just the combination of these two things. To be specific, since the current that flows is inversely proportional to the resistance and directly proportional to the EMF, then the current is directly proportional to the product of those two things. Get a better pen here. So I is equal to the EMF over the resistance. Okay. And so this relationship here is the relationship that we're after. This relationship answers our question, given that battery, given that much resistance to flow in the circuit, what current can I expect to flow? This is the answer to the question. And this particular relationship was first described by I think, Dutch physicist, I might have to look that up, named George Ohm. And George, I think it was George. Anyway, Ohm is his last name. And it is misnamed in his honor. It is called Ohm's law. But it is not really a law, not like the law of conservation of energy, for example. It's a better way, and because this relationship, the reason I'm hedging on this, is because this relationship simply doesn't hold for lots of materials. Okay, it basically only holds for really good conductors and values of resistance that aren't too large, and it only holds as long as the temperature of the circuit doesn't get too hot. Temperature, where does temperature come into it? We'll talk about that. So as long as R isn't too big, as long as the EMF of the battery isn't too big, as long as the current isn't excessively large, then this relationship holds good. But if any of those three things are violated, then this relationship is then the relationship between the current, the EMF, and the resistance is no longer this simple. And so that's why it shouldn't be called a law. Okay, it should be called Ohm's observations about a limited collection of materials under a limited set of circumstances. Somehow that's not quite as catchy as Ohm's law. But please be aware, Ohm's law is only applicable over a comparatively small number of types of materials: copper, silver, gold, aluminum to a lesser extent, over a limited range of potential differences or EMFs. Yeah, but on the other hand, when it works really well. What are we talking about? For example, if I have an EMF of, let's see, if I have two batteries that are marked 1.5 volts, two D cells marked 1.5 volts, I said a few minutes ago that stamp on the side is the EMF, not the potential difference. Okay, and so if I have two of them, so let's see, what do we have? Two D cells are connected or wired in series. What does that mean? I'll show you. And we have a light bulb. Let's see. Yeah, okay. And the light bulb's resistance is 0.3 ohms. Okay, I'm going to stop here and talk about that, because that, of course, is the unit of resistance. What? Resistance, 3.3 ohms. Okay, so R, I said, is a number that describes how much resistance to flow there is in your circuit. Okay. The effect, as I've also said, of the resistance is to decrease the more resistance you have, the less current you get. The unit of resistance, not only did Ohm get this mathematical relationship named after him, he also got the unit of electrical resistance named after him. And so the unit of electric resistance is called the ohm. Okay, and the ohm is actually defined, as it turns out, it's defined to be, so 1 ohm is 1 volt of potential difference, or 1 volt of EMF per ampere of current that flows. Okay. Normally, the symbol for the ohm would be given the capital letter of the first letter of Ohm's last name, just like the farad after Michael Faraday is capital F, and the Newton capital N. So too, this should be capital O. The problem with that, if I used, and this is true by the way, what I'm about to tell you is absolutely true, we didn't want to use the letter capital O to indicate resistance, because then I would have had to say a resistance of let's say a resistance of 12 ohms. That's a resistance of 12 ohms. No, I think you can see the problem. So it turned out, no, we don't do that. The symbol for electrical resistance is actually this thing. That's the Greek letter omega, capital omega. And the ohm is given this symbol for 2 reasons. One, it sort of vaguely looks like a capital O, but also, and again, true story, it's because this letter, pronounced omega, is the same as its first syllable is, well, ohm. So there you are. Right, so that's why I wrote over here. So the resistance of our light bulb is 0.3 ohms. So then, of course, the question is what current flows. Okay, well, normally I don't draw them like this, but I will here, and then I will. So there's a D-cell battery. Bottom is defined, well, for a single battery, 1.5 volt difference of EMF. Okay, so this has an EMF of 1.5 volts, and I'm going to attach another one. Okay, so this is 1.5 volts of EMF. This is 1.5 volts of EMF. Okay, so the total EMF, the potential difference from down here, which we'll define to be 0 volts, then it's up here, the potential difference is, I'm sorry, measured relative to here, this is where 0 is going to be. The potential difference at this location in space is 1.5 volts. The potential difference, the EMF at this point in space is now 3 volts, measured relative to here. Okay, and then I go and I attach it to a light bulb and then complete the circuit. And now what current flows. And this thing has some amount of resistance, 0.3 ohms. And Ohm's law then allows us to calculate the answer to the question. But before I do, I want to show you the schematic version of this thing. And it would simply be, you might think, oh, I draw 2 of these little symbols, and occasionally you will see people do that, but more commonly, we simply label this as 3 volts. And it, by the way, doesn't matter where in your schematic circuit diagram you place the resistor, as long as it's electrically equivalent, which it is here, and which you can see, by the way. You look here, the current will flow from the high potential, and it will fall down to the low potential, and of course that will happen spontaneously. So there's our current I. And the same thing is true here. Normally we don't draw 2 of these symbols, we just draw the one symbol and label it with how big the potential is, or the potential difference, the EMF. Okay, that all said then, and I talk about that because frankly that's the hardest part of the problem. The actual calculation of the current is trivial. The current that flows is simply the potential difference created by the EMF, and so that's 3 volts over 0.3 ohms, and that works out to be 10 amps. Is that right? 3 over 0.3 is 1 over 0.1, and so yeah, so that'd be 10 volts per ohm, or 10 amps. Okay. And basically, though, what that suggests, 10 amps, by the way, if you don't have a standard for comparison, there's no reason for you to know this, but it turns out 10 amps is a pretty large current, which tells you that the resistance here is this is a pretty small resistance to flow, and that's true. Okay. This is an extraordinarily small resistance for a light bulb. Most light bulbs are significantly higher than that. I sort of chose a random number. All right, so that's basically Ohm's law. There's more to say about Ohm's law, and I'll talk about that. And I'm now in a position to talk about the difference between the potential difference V and the EMF E. What's the difference between them? I've sort of hand-waved my way around it. Now I can tell you. And we'll also talk about what specifically happens when the current flows through the resistor. And we'll also talk about, almost parenthetically, why did I write I all over this circuit, at every point in the circuit, and why did I write only I? I mean, for example, why didn't I have I1, I2, I3, and I4, and so on? Why is it just I? So all those questions and more in the next video or two. This is so exciting.